Hey viewers, welcome back. So today we're going to look at the two following expressions. The first one says x to the 8th power plus x to the 7th power plus 1. And the second one, we're going to change the first term into x to the 11th power. So what are we trying to do? Of course, we're trying to factor out. But wait a second. We only have 3 terms for each expression. And the power are actually beyond the third power, meaning that for example, the leading power is 8 and 11 respectively. Is it really possible we can factor it out? And of course, people might complain that, well, if we think it as an equation, we can always solve for x and then we'll be able to factor out. And of course, if we try to do it that way, yes, we can always do it. We can always make an answer. And it's always factorable. But unfortunately, if we do it that way, usually the answer will end up with some not rational number, irrational number, or sometimes it might be even a non-real complex number. So the question is, can we really factor these two terms out with the coefficients that are only integers, so that we can always try to end up with something that is kind of nice, that we don't have to see any irrational numbers in the coefficients or even imaginary units. So before we move on, you can just pause the video and try yourself first and see you actually can come up with the answer. Done? Alright, so let's talk about the first one, which I personally think is easier. Because once we see the trick in the first one, we'll be able to do the second one almost immediately. So here's the deal. If you have ever seen the expression like this, for example, x to the 5th power plus x to the 4th power plus 1, most of the time we might think, again, there are 3 terms only, but then the exponent is the 5th power, which is way bigger than 3. It might seem not possible to factor out. And it'll be right if we are trying to change the 4 into 3 or maybe 2, something like that. But if we have something right here in particular form, we can actually try to factor out into 2 polynomials that the coefficients are integers. How do we do it? Well, here's what we are going to do. Instead of just putting the 1 right here, I'm going to put it on the last row here. And then here is what I'm going to do. Consider that here is x to the 5th power, and then we end up with x to the 0 power, which is equal to 1, of course. We will say that if we don't have the 0 coefficients here, let's say if we have something non-zero for the x to the 3rd power, x squared, and x respectively, we will be able to end up with 6 different terms. Meaning that if we fill up these here with, of course, doesn't really matter, but for example, if we just put 1 copy for each one, then we will end up with 6 different terms. And why does that help? Because now if we try to put a specific value or a specific coefficients for each term that is missing, we will be able to see that at some point we'll be able to factor out the new expression. For example, if we put coefficients 1 for each missing term, we now see that there are 6 terms in total, and in fact, we'll be able to factor out as the following. In here, we can just group the first 3 together, and then factor out the common factor, which is x to the 3rd power, so that we now remain with x squared plus x plus 1. Of course, we have the x to the 3rd power here. And now if we try to factor out or group the second row together, we actually end up with the same thing, x squared plus x plus 1. So this means that we can now factor x squared plus x plus 1 to give us this expression. And now we'll be able to factor out. And of course, we cannot just simply add some terms in it. So since we add one copy for each of the missing term, we of course need to substitute, no, we actually need to subtract it back. And if we subtract it back, we actually get this expression here, which has a common factor x, or negative x if you take out the negative as well. Then we'll end up with x squared plus x plus 1. Aha! We have something in common again, so that we can actually factor out. And therefore, we now get the expression x to the third power minus x plus 1 as the other factor. Meaning, even there are only 3 terms here, if we are actually ending up with a right position, we will be able to add something, of course, and we need to subtract it back, so that now we'll be able to factor out. So how does that help? Well, if we look at this example here, we can see that this time we're not only missing the third power, second power, and the first power, but we also missed the sixth power, fifth power, and fourth power. So we can just try to put those in and fill up to get the expression x to the 8th power plus x to the 7th power plus the 6th power, so on and so forth, until we hit the first power, and then we'll add it with the constant 1 that start off with. And again, of course, if we add the red part, we need to subtract all of them back. So now we can actually factor out the first row, because now we have 9 terms. We can group them into 3 groups of 3 terms. So we will get x squared plus x plus 1, and we're going to group it in this order here. And for each group, we will be able to factor out x to the 6th power, x to the 3rd power, and 1 respectively. Now, if we look at our second row, we can in fact do the same thing by grouping it this way, since there are 6 terms consecutively. And we will be able to group it into two groups of 3 terms. Each group will actually give us x to the 4th power and x respectively. So, ladies and gentlemen, we can just fill in with minus x to the 4th power and minus x. And that's how we factor out the first expression. Very nice, huh? So, what happens if we change the 8 to 11? Here, we no longer have the first 2 terms. We have the second term that is not in the second highest order. So instead, we actually have the second term in the somewhere in between. Are we able to do it? Well, let's see. We started off with 11. So from 11 to 0, there are in total 11 plus 1, which is 12 terms. And now we end up with 3 terms, so we should expect missing 9 terms, of course. So what does that mean? It means that if we can actually have 3 terms or multiples of 3 terms consecutively missing, we will be able to factor out. So in fact, we have x to the 11th power plus x to the 7th power. But in between, there are 3 terms missing, and there are exactly 3. X to the 10th power, 9th power, and 8th power. So if we try to use the same method by grouping into 3, we now have exactly 3 missing in the middle. So we will be able to factor out and get the subtraction part. Similarly, we have x to the 6th power, 5th power, all the way down to the 1st power missing. And here again, we have 6 terms missing. So we will be able to factor out into 2 groups of 3 again and be able to get what we need to subtract. So, ladies and gentlemen, we can actually factor them out into x squared plus x plus 1, the 3 consecutive terms, times. Now, remember the red part is something that we're missing. So if we fill it up, we'll end up with 11 plus 1 term, so it will be 12 terms. Then if we group by every 3 terms, we will get x to the 9th power plus x to the 6th power plus x to the 3rd power plus 1. And now we just need to subtract back the terms that we actually filled in. So first we have the red parts on the first row, which gives us x to the 8th power. Second row, we will group it into 2 groups again, like this. And again, we'll get x to the 4th power and x respectively. And therefore, we will be able to get our answer as we try to factor out such expression. Alright, that's it. I hope you enjoyed this video. I'll see you guys in the next video then.